Yeah. So actually, before we talk about detecting sort of wave dark matter, I want to discuss some theory issues that have come up over time, and also give you kind of a bit of a perspective on sort of detecting dark matter and what it really means. So as Marco said, right, if you look at the observational bounds on dark matter, which is what we should be guided by, dark matter's mass can be anywhere from about 10 to the minus 22 eV, okay, all the way. You could put it as a Planck scale thing, whereas Marco said, if you want to understand, if you put a sort of a theory limit, okay, a fundamental particle above the Planck mass would be like a black hole or whatever. But observationally, you could even think about composite dark matter, which could go all the way to something like 10 to the 48 GeV, or around 10 to the 24 grams. So this is a very, very large part of parameter space. And the question becomes for us to figure out what is the optimal way to search for this kind of dark matter, right? So given the vastness of this, in these lectures, we are largely focusing on ultralight dark matter, which is sort of dark matter below the mass of around an EV, okay, 1 to 10 EV roughly. And, so that's kind of what, we're focusing on. There's nothing wrong in thinking about dark matter all the way in this mass, but this is our goal. Ultralight dark matter. So before we get into the details of how to detect the dark matter and what it should be, right, I think one question that we must ask is, since a lot of you are theorists, questions like, is it reasonable, right, to search for dark matter that is this light, okay? Now, I want to make these sessions sort of interactive, right? And in some sense, I could stand here and drone on for 6 hours and keep myself entertained, which I usually do. But if you're not actually engaging, it's not that useful. So I want to kind of ask the question. So since a lot of you are theorists, right? If someone comes and tells you that the dark matter mass is like 10 to the minus 22 EV, okay? What kinds of questions should you as a theorist ask them? Yeah. But we've already known observationally if the mass is below 1 eV, it cannot be a fermion, right? So this is definitely at this point bosonic, and actually it's important, right? So indeed, this is a boson. So some of the questions you may ask are actually peculiar and specific to boson. So let's say I'm telling you that the mass is 10 to the minus 22 eV, so it's a boson, okay? What's the next kind of question you must ask? Yeah, so, I mean, someone gave it to you already, okay? So that is a dark matter. Yes, someone was saying something else. Why is it that light? Exactly. So the question becomes, why is it light? Right? So broadly speaking, this becomes a question about a topic called naturalness. Right? And there's a lot of blah blah about naturalness. And should we care about naturalness? Should we not care about naturalness? Should people below a certain age think about naturalness? All this kind of stuff. Okay. So, but I want to put some teeth into this, right? Why? Because if you're thinking about detecting dark matter, right? It means building an experiment. It means going and actually doing stuff in the world. And those things cost time and energy, right? And so if you're going to spend your time doing this stuff, there better be an actual reason why you're doing this. Okay, so let's make naturalness, toothy, right? What does it really mean? Okay, let's think about a variety of atomic states, okay? What is the typical energy of an atomic state? Yeah. 50. 10 eV, let's call it, okay? Fine. What about nuclear levels? What are some typical energies of nuclear levels? What should it be? Huh? MeV, exactly. So a typical nuclear level is about an MeV. Okay? Various excited states. And that comes from a combination of two things. There is like QCD binding energies, which are order a few MeV. And there are electromagnetic contributions to the energy, and those are typically about a few MeV. And so typical nuclear levels are about MeV. Okay? Now, people have gone around in the world and they have measured various nuclear properties. Okay, and more recently, people have discovered that in thorium-229, okay, there is a nuclear level that's about 8 electron volts in energy. Okay, that's a measured fact about the world. All right, and this is useful for a variety of things called nuclear clocks, etc., which we won't talk about today, but this is just a fact, right? So the way you get ADV is because of a cancellation between the nuclear QCD contributions and the electromagnetic contributions, right? So ADV is equal to, QCD minus electromagnetism. So that's a fine tuning, if you will, right, between these dramatic things. Okay? Now we know this exists. Okay? So now comes the question. Suppose I want to go and search for various nuclear levels in the world. Okay? And I'm an experimentalist, and you guys are the funding agencies. And I come up with you for a proposal where I say, hey, give me money. I want to find a nuclear level that is, let us say, 10 to the negative 22 EV, okay, above the ground state. How many of you will fund me? Nobody. Jesus, tough crowd. Okay. All right. How about the following? Okay, I want to go and find various materials in the world, metals and things of this kind, and I want to measure the resistance of these metals. Okay, and I have already done this following thing. I've gone around and some materials, let's say, I measured the resistance. I found the resistance to be 10 to the 9 ohms. In some materials, I found the resistance to be 1 ohm. And in some, I found the resistance to be 0 ohm. Okay? And I now say, look, give me money. I want to find some materials where the resistance is 0 ohms. Okay? How many of you will fund me for that? A lot of you. Okay, good. So what is the difference between 10 to the negative 22 electron volts for the case of the nuclear levels versus 0? Yeah, but you're correct that, but okay, instead of making it 0, I could have made it very small, right? So it's not like continuity per se is the actual reason, right? Because in fact, in some sense, if you look at it, you might say, look, there is like a discretum almost, right? There is stuff at 10 to the 9 ohms, there is stuff at 1 ohm versus stuff at 0. What is it that actually distinguishes these three resistances? Huh? Band structure, exactly. So what is true is that if you think about resistances, we have a theory, right? We basically say that I can go and look at the quantum states of materials. Okay, there is this block wave or whatever, which we'll get to at some point again for a different reason. But there's an actual theoretical understanding which tells us that there are actually different kinds of materials, where if there is a certain quantized set of levels, they're called bands. And if your band structure is a certain form, there is a non-zero resistance, and that would be an insulator. So an insulator, the resistance would be 10 to the 9 ohms. Well, for a metal, it's like 1 ohm, whereas if there is an appropriate like mass gap and stuff like that, I get a superconductor where the resistance is actually 0. Right? So if you think about this and the connection to the nuclear case, in the case of the nuclear levels, okay, yes, it is true that I have this dramatic cancellation between QCD and electromagnetism. And the way we would understand that is basically say that, look, there are order 200 nuclei, and these nuclei have a large number of levels, right? And indeed, the typical nuclear level that you find will be MeV. But just from statistics, okay, it is not unreasonable that there is some number of them where the cancellation is dramatic, and that dramatic cancellation gives me something at ADV. Okay? However, it would be truly insane if you went and found two nuclear levels that cancelled and you found a level at 10 to the minus 22 EV, right? Because if someone actually did that, I would be shocked, right? So here the point is, this is a miraculous cancellation. Whereas in the case of different metals, it is not that there is some miraculous cancellation that actually led to a superconductor existing, right? Here we actually have a mechanism where it is the existence of this mechanism that tells you that hunting for things with zero resistance is not a fool's errand. Okay? So that is exactly what we mean by naturalness, where we basically say that, look, if I think there is some thing in my world, whatever it is, right? It's not like the Higgs mass or a boson's mass or something specific, right? Pretty much any phenomena that you're dealing with in the world, you can go and calculate, right, what its typical behavior ought to be. And if you find something dramatically different, it should make you think about what's actually going on, and then you may go and hunt for a mechanism. Okay? So that's why anyway, the bottom line, you get it, right? Some things are natural, some things are not natural. Having said that, okay, so I've kind of scoffed at this idea that you should go and look for 10 to the minus 22 EV, right? Let's ask the question prior to this, which is that how did people go and discover this 8 EV excitation? Did they know it was going to be there? No, right? So if you're again going to go and spend your time, right, trying to figure out what nuclear levels there are and what nuclear levels there aren't, okay, what really happened was the fact that people were going and making various measurements, and by making various measurements, they accidentally found there is one at 8 EV, okay, even though it's highly unnatural, right? So if someone had come to you prior to them discovering 8 EV and then asked you the question, hey, would you fund a person's time to go and find an 8 EV level, what would you have done? Would you have funded them? No, right? Even though those things actually exist, right? So the funny thing about physics, right, is that we can say all the philosophy we want, but at the end of the day, this is an experimental subject, all right? And if you're an experimental subject, the real problem is the fact that you're not going to figure out what is in the world unless and until you go and make measurements, right? And I would point out the following thing, which is that even in the standard model, right, we know there are unnatural things like the cosmological constant. There are also unnatural things like the Higgs, right? Those things actually exist. And the fact that theorists do not have explanations for them does not preclude their existence, right? So for me, this entire business of is it natural, is it not natural, or whatever, okay, that's a job for the theorist, right? As a theorist, if you come and tell me there is something with 0 ohms, I will go and think about why that is, okay? I don't spend much time thinking about an 8 EV excited state in the nucleus simply because I know there are dozens and dozens of these nuclear states, so it's not unreasonable that one of these cancellations actually exist. But none of this should actually preclude me from going and searching, right? The question of searching becomes a question of how expensive is it to search and how difficult it is, right? So it's in fact true that if I ask myself that, look, if someone came to me with a proposal to go look for various nuclear levels and the proposal cost, I don't know, a few $1 million in a few years, I would say, yeah, go do it. Who knows what you'll find? But if it cost them, I don't know, 10 billion and 100 years, that would be dumb, right? So for me, this is a very simple game, but I basically say, when I think about this huge dark matter parameter space, sort of switching it back to dark matter, right? If it's ever the case that some experiment somewhere here, anywhere, whether it's an experiment I have proposed or an experiment someone else has proposed, it's someone's theory, whatever it is, right? If that experiment is going to cost you, I don't know, 10 billion and 30 years, maybe not worth it, right? Because it's a huge parameter space and you don't know which one to pick. On the other hand, if it's some experiment that costs you a few million in a few years, you should do it. Okay? So that's a very practical way for me to think about what experiments are worthwhile, what experiments are not worthwhile. So I want to set that out just to give you my own perspective on this field, largely because I will be talking about a large number of experiments that live in this part of parameter space. Okay? Any questions about this? Good. Okay. So the next topic I want to discuss is a little bit more about the wave dark matter. I want to kind of build on topics that Marco kind of already addressed. And I want to kind of distinguish how the wave dark matter story is fundamentally in some ways different from the particle dark matter story. Okay. So since you guys all had, why we assume boson? That is because of the fact that if they were fermions, they cannot be this light. Okay, so I don't know if Marco discussed that. Did you discuss it, the Tremaine gun? He did. So you were probably asleep. That's okay. Okay. So here is the, I mean, I was asleep as well. Otherwise, I would have known that Marco said it, right? So here is the main thing, right? That basically what we know about the dark matter is its energy density. That's a known fact, right? Now, given the energy density, the number density is always the energy density divided by the mass. So if the mass of the dark matter gets very small, the number density will go up. Okay? So the next thing we know about dark matter is that dark matter fits in our galaxy. So the dark matter fits in our galaxy, you basically have to say, look, I have these various energy levels that it can actually sit in. It's like a particle in a box. And all you're basically saying right now is that, okay, look, if I have a very large number density, right? If it's a fermion, I cannot put more than one, spin up, spin down in a level, so that will overfill my levels, right? So anything below 1 eV has to be a boson. All right, good. By the way, it's perfectly okay for people to repeat stuff and ask questions again, because indeed, most of you will fall asleep, so it's okay. All right. It's a difference between being someone like me who's been a professor for a long time and has taught and knows how many people fall asleep versus Marco, who's young and fresh and believes people are always paying attention. Okay. All right. So let's talk about particle dark matter, right? So in particle dark matter, the basic kinematics you actually have is the following. There is some nucleus, and there's a dark matter that comes and scatters, right? When it scatters, it deposits energy, right? That's what we detect. Okay. So if the dark matter, let's say, is light, okay, its mass is less than let's call this m chi, let's call this a nuclear mass. Suppose the mass of the dark matter is less than the mass of the nucleus, okay? Then, there's an elastic collision, and we know how much energy is deposited, right? We'd basically say, look, this is like an elastic collision, this guy is lighter than this, so the energy that is deposited in the nucleus goes as m chi v squared over the mass of the nucleus, right? This is some elastic collision process that's actually happening. Hopefully people are familiar with this, right? And what you know from this formula is that as the mass gets smaller and smaller, the amount of energy that is being deposited is tinier and tinier, right? So if you now think about this formula for a second, and you look at very, very light dark matter, right? Fundamentally, it becomes clear that if what you're going to be doing is scattering of this kind, the energy that's going to get deposited is going to get ludicrously small, right? For example, if the mass is about 10 to the minus 22 eV, just to go all the way to the extreme, the energy that you're going to be depositing, if this is what's happening, it will be 10 to the minus 22 eV, okay, times the velocity of dark matter that's 10 to the negative 3 squared over the nuclear mass, let's say it's 100 GeV, which is basically a number very close to 0. Right? I'm not going to calculate that, but obviously small. So clearly it must be the case that if we have any hope in hell of detecting this, that what is happening is not this process, right? What's going on cannot be this. But how can you possibly avoid it? Because indeed, is it not the case that when you have scattering, what you must be doing is conserving energy momentum, right? After all, I didn't assume anything else. I just said, look, the dark matter comes, it scatters. That's what I'm going to do. Okay? And the moment I say those words, I am bound to accept energy momentum conservation. So if I'm bound to accept energy momentum conservation, how could I get a different answer? Yeah. But the dark matter is non-relativistic, right? And even if you treat it relativistically, it is in fact the case energy momentum is still conserved. Yeah. Well, how would the material help? Because the material is going to get heavier and heavier. Right? You don't want to make the denominator big in this story. Collective interactions, you say, okay, but like in what way? So if I have a large number of particles, will that necessarily help? Because remember, it's all very well to say collective, but the fact of the matter is, right, that if the collision rate for any one particle is very small, right, then, because, if you think about dark matter, right, the coupling is so small, that if the chance that one particle scatters with you is very small, the chance that n of them will simultaneously scatter is even tinier. Yeah. Mm. Good, good. You said the magic word, coherent. What does that word mean? Uncountable. Okay, good. All right. So let's unpack those words, and that's exactly what I wanted to make clear, right? So there's something about ultralight dark matter that people often glaze over, but is actually fundamental to our strategy to detect it. Okay. So let's think about two kinds of waves. Yeah, I want to talk about gravitational waves as well, but electromagnetism we are much more familiar with, right? So this is something that's actually important to understand. So let me have a source of radio waves, okay, which is like a antenna, right, or something that I draw current back and forth through. All right. So and this thing is producing an electromagnetic wave. So it's like a radio station, right? In which I listen to my favorite whatever music or something. And so how do I detect this wave? Well, what I do is I have an antenna, right? And the radio wave comes in, and the radio wave is going to drive currents in this antenna, and I convert that to something that goes to my ear. There's another kind of radio wave in the world that we like to detect, which is called the cosmic microwave background, right? How is a detector of the cosmic microwave background different from a typical radio station that I have? Or is it exactly the same? You think it's the same? What does that mean? The size comes down to a question of statistics and stuff like that, right? So yes, it is true that my radio station is often close to me, so my antenna doesn't have to be as big. But you think there's fundamentally no difference between what you're detecting in a radio station versus a CMB detector. Okay. All right. Good. Let's see if that's truly correct, right? So in a radio station, okay, what kinds of information do I get from the radio wave? There's clearly an amplitude, right, which is like essentially how strong the radio signal is, because the faster, like further away it is, the amplitude gets smaller and smaller. So that's something I need to deal with. But what else do I actually truly get from a radio wave, from a radio station? The phase, right? So if I think about the electromagnetic wave coming out of a radio station, I will write that as a classical field. I'll write that as E naught, okay, some amplitude, times cosine omega t minus omega minus kx or something, plus some phase delta phi, okay, which of course changes in time and space. And in fact, all of the information from the radio wave actually is contained in the phase, right? Because when I'm talking and you guys are hearing it, right, this goes through some blah blah here, but it's actually the phase that gives me all that information, right? Now in a CMB detector, what is the phase of the light that is coming in a CMB detector? It's constant, he says. Okay, what constant is it? Is there even a phase in the CMB? You think there's a phase? There's a temperature, right? A temperature is a statement about intensity. So you're absolutely correct that there is intensity information that's all living in E naught. How much power there is, right? That's what we measure. If you go and talk to a CMB guy, right? The CMB person is detecting temperature fluctuations. They're detecting polarization, right? Like which direction the electromagnetic field is in. But nobody's talking about the phase of the CMB, right? And that is because the phase doesn't exist. Okay, it's actually the constant zero, right? So what is it that is different? Yeah. Individual quanta. Yeah, so why could you not look at collective events for the CMB? Okay, so what about the sun? Right, so let's think about the two different kinds of light. One is a laser, which people have in their lab, right? There's an electromagnetic field associated with the laser, and that is indeed some E naught cosine omega t minus omega x. I can associate that electromagnetic field with a laser. The second is the sun. Okay, the sun is very big and very, right? There's a lot of photons. Would I associate a similar classical electromagnetic wave with the sun's photons? A laser has a phase, right? There's a laser phase, noise, all the stuff. But with the sun, would you associate that? No. So what is it that is similar quantum mechanically between the light emitted from the sun and the CMB? Random phase, right? So they're both what we would call thermal sources. Okay? So this is something that I wanted you to understand properly, which is that people often make this sort of loose description. They often say, oh, ultralight dark matter, it is a coherent state because it's a large occupation number, etc. That's an often stated thing, but it's not actually true. There is a pretty important difference between what makes something quantum coherent, okay, which is the sort of thing we're talking about when it comes to ultralight dark matter, as well as the light from a laser or a light from a radio station, versus other quantum states that you have, which are clearly the kinds of light that we get from the sun or light that we get from the CMB, which are more thermal states. Okay, and that's a quantum difference, and I want to spend a couple of minutes talking about that before we describe in detail how we can detect these things. So let's distinguish between two things. Okay, one is called a coherent state, and this will be true for the radio station, lasers, and ultralight dark matter. And the other is going to be, let's call it a Fock state. And this is going to be true for WIMPs, okay, and then sun, okay, and even like the CMB, right? So before we get to quantum field theory or whatever, which I don't want to spend too much time on, let's just talk about these things just with a simple harmonic oscillator, right, which people understand much better. So I'm going to talk about the quantum mechanics of a simple harmonic oscillator. So, we all know the potential. V of x is some 1/2 kx squared, something of this kind, right? And I can think about a classical version of the simple harmonic oscillator, which we've all solved, and a quantum version. So classically, we would say there's an equation of motion, which is basically x double dot is equal to negative kx over m, right? That's some equation. And then there's a solution to this thing, which is basically x of t is some amplitude a naught cosine omega t. Okay? Quantum mechanically, I solve the Schrodinger equation, right? So I'll go and solve the equation I d psi dt is equal to h psi. And we all know how to solve this problem, which is that I will write this harmonic oscillator, okay, in terms of a and a dagger, the ladder operators. So I can write this Hamiltonian as a dagger plus like 1/2 or something, okay, with some omega up front and times psi. And we all know what are the energy eigenstates of the system. We've all solved for this, right? So the energy eigenstates of the system, which I guess I'll write below here, okay, are these, states that you construct from a and a dagger. So you say there's a state 0 called the vacuum, which is annihilated by A, and there are various states. A dagger, okay, acting on this will give me 1, and so on and so forth, right? So those are the energy eigenstates of the system that we all know about. So now comes the question, okay, I have a simple harmonic oscillator in my lab, I let it go and I watch it go back and forth, right? I want to know what states of the quantum system, the quantum mechanical analysis, actually describe this back and forth motion that I see with my eyes. Okay? Are they the energy eigenstates of the system? No, right? An energy eigenstate doesn't change in time. So clearly the fact that this thing moves back and forth tells me that the classical motion that I'm seeing is not actually due to the energy eigenstates. It's some superposition of these energy eigenstates, obviously. So that's what. So let's call these guys. Okay. So this is the. We'll call this Fock states. So the energy eigenstates of the harmonic oscillator, let's call them Fock states. They do not represent the motion of the simple harmonic oscillator that I see with my eyes when it moves back and forth. Right? So the question becomes, what kind of quantum state represents the classical motion? Right? That is basically, I have my spring and I sit there and this thing moves back and forth that I can see. Yeah. Okay, eigenstates of the lowering operator. Very good. So let's be a little bit clear about why that is. Right? What truly distinguishes the classical motion, right, is the fact that the classical motion that you see has a well-defined phase. Right? When I say cosine omega t, I'm sitting there and saying, look, at time t equal to 0, this guy is there, this guy is there, so on and so forth. I can literally see this moving back and forth. Right? So the classical motion is really a state where the phase is very, very well known. Okay? So I want you to connect that with the electromagnetic wave stuff we were talking about earlier, where we said, look, if I'm thinking about a radio station, radio wave, or a laser, or things of this kind, these are states of the electromagnetic field which have a well-defined phase, right? So they are the classical things we're thinking about, and so there should be a connection between those kinds of states and the classical states of the harmonic oscillator, okay? And now comes the second part of the distinction, which is basically how are these Fock states related to the thermal states that we talked about, right? So I'm going to put all of this together for you. All right, so let's connect these things. So first of all, the point I want you to notice, right, is the following thing, right? When I think of my classical equations of motion, x of, this x double dot is equal to whatever, dv dx, right? Fundamentally, where do those equations come from, right? What we should understand is that in reality in the world, there's only one equation, Schrodinger equation. So everything in the world, of course, satisfies the Schrodinger equation. So even when I'm actually going out there and figuring out how my simple harmonic oscillator is supposed to move, I'm not actually supposed to use Newton's equation, because Newton's equation is a classical equation. Who cares? It's not right. Okay? But as you undoubtedly know, Newton's equation is correct. That's why Newton is famous, right? So the correct way to think about all this is to basically say, look, I know the Schrodinger equation is the correct equation of the world. And what is true is that whenever some quantum state obeys the Schrodinger equation, automatically, through something called Ehrenfest's theorem, right? If I go and calculate the expectation values of various quantum mechanical operators, I will find that this is true. Okay, I'm not going to go through the derivation because I assume you've at least heard this in your undergrad, right? So this is the correct connection that Ehrenfest's theorem tells you, that whenever a state obeys the Schrodinger equation as an identity, automatically, you don't have to do anything, okay? Identically, it is the case that the expectation values of various quantum states will obey the corresponding classical equations. Okay, now, but this must make you think again, because I was trying to make this connection saying, look, I've got my classical, motion, A naught cosine omega t. That guy does not look like the energy eigenstates of the harmonic oscillator, right? Clearly. So I was trying to make some big deal around this being a little different. But is it not the case that if I compute these equations for the energy eigenstates of the system, which I can do, right? Should the energy eigenstates of the system also not obey the corresponding classical equations, right? Because all that was necessary for Ehrenfest's theorem is the requirement that a quantum state obey the Schrodinger equation, which of course every energy eigenstate will obey the Schrodinger equation, right? So is it not the case that if I take the harmonic oscillator's energy eigenstates, substitute them here, they obey the Schrodinger equation, then as an identity, they will obey the corresponding classical equations. Shouldn't that be true? It should be, right? So even though it is true, let's now explicitly calculate it and see what it actually implies. All right? So let's do this now for the energy eigenstates. So to do that, remember that the X and P, right? There's some linear combinations of A and A dagger. I don't remember the exact combination, but it's A plus A dagger, let's say, and X is like A minus A dagger, right? Probably I've messed up the signs. Is the opposite. Very good. Okay. So, what? Yeah, whatever. Right. Okay. Let's now compute what this operator is. Let's say for a large occupation state. Okay, so large occupation state meaning that when I take my harmonic oscillator and if I have A dagger acting n times on the vacuum, I get the state n, right? That's got like n quanta sitting in it. N can be super duper big. Okay, it's a highly occupied state, but I want to calculate what this quantity is, n, p, n. Okay, so n is an energy eigenstate. So this is simply n A minus A dagger n. What's that? Well, that, yeah, but like what is it in what number is it equal to now for this specific state? 0, right? Because essentially A dagger acting on n will give you n plus 1, that acting on this will give you 0. A acting on n will give you n minus 1, that again gives you 0, right? So this is equal to 0. Similarly, if you calculate n xn for exactly the same reasons, is also 0. Okay? So now if you go back to this equation, the classical equation, right? The equation is trivially true, right? Because what's happening is that the expectation value of the momentum operator is 0, the expectation value of x, whatever appears there, is also 0. So the equation is correct, except it's got no useful information, because what you're actually learning is that these expectation values do not time evolve. You get 0 equal to 0. Okay? Whereas, what you are usually used to seeing when you're thinking about the harmonic oscillator, the thing moving back and forth, is that at every point in time, you're actually able to go and calculate momentum as a function of time, which is non-zero, the x as a function of time, which is non-zero. So then you have to ask, okay, what are those states for which those things have non-trivial and well-defined, time evolution? Okay, so this is exactly what the dude was talking about, which is that there are specific states of the harmonic oscillator, which are called coherent states. You've probably seen this before in your undergrad curriculum, which have the following property. So you say, look, I have a state alpha, which is an eigenstate of the annihilation operator. So this A acting on alpha is some eigenvalue, let's call it lambda of alpha, okay, acting on alpha. Okay. Now, is A Hermitian operator? No. Okay, so there's no reason why this lambda needs to be real. It could be complex. That's fine, right? Now, usually in quantum mechanics, we are trained to think only of Hermitian operators. Now, that's true because if I think about like various physical observables that are tied to this, they come from Hermitian operators. But there's nothing wrong with an operator per se being non-Hermitian, as A actually is. It can still have an eigenvalue. That's okay, right? So it turns out you can construct such states. Okay, I'm not going to go through the construction. You can look it up if you want. So these kinds of states, alphas, okay, these are called coherent states. Okay, and for these states, right, it is the case that if you go and calculate A plus A dagger, which is like position, for example, This will give you something non-zero, and so on and so forth. You can go and calculate what that is, right? And you can actually show that these states, the coherent states, these are the things that actually correspond to your usual classical motion, right? So there's something important to understand. So the key distinction I wanted to get to here is the following, right? From the simple example, that just because you are in a state of high occupation does not mean that you have classical behavior, right? The Fock state with n particles, n quanta in it, is a state of very high occupation, but it has no associated quantum phase, meaning that anytime I calculate nx, the expectation values of these guys, they just give you zero, like nothing is actually physically moving in those cases. Whereas if I do it for a coherent state, I get something non-zero. Okay? All right. So let's now go connect this to the electromagnetic cases as well. Since this is not a full-time lecture on quantum field theory, which I'm happy to give you, but that'll take us too far off course. I'll just assert what the connection is, right? So the connection comes the following way. I think like Marco briefly alluded to this in his lectures, which is that when I think about a quantum field, okay, what do? I say phi, the quantum field for something, okay, is written in terms of some creation and annihilation operators. I write integral d cubed k, for example. There's an ak e to the I k dot x plus a dagger k e to the minus I k dot x. So this phi of x is an operator, and the a and a dagger, those are actually various creation and annihilation operators, okay? And what you guys have seen before is that when you go and create particles, right? A particle is nothing but a state that is annihilated by ak. So now I say if I have an a dagger k acting on the vacuum, I get a state that is 1k, right? That basically means a dagger k acting on the vacuum creates a single particle of momentum k, right? If you remember that from your field theory notes from earlier, okay? So notice that this is exactly like my Fock states here, okay? So these states, which are states of definite particle number, they correspond to the Fock states of the harmonic oscillator, okay? Similarly, I can also construct, because this is at the end of the day just a harmonic oscillator problem, I can also construct a new state, okay, which is like ak, let's call it alpha sub k, which is an eigenstate of the annihilation operator, call it lambda, okay, lambda alpha of k or something, alpha k. So this becomes a coherent state. Okay, so just like the harmonic oscillator, a quantum field is also allowed to have coherent states. Okay, and now we can try to connect these two cases. Let's now talk about the difference in scattering. Okay, now that we've jumped into quantum fields, difference in scattering between a coherent state and a Fock state. Because that's what I was going for, right? Why is there an energy momentum conservation issue? What is the difference in how scattering works for a coherent state versus a Fock state? Yeah. Yeah. Yeah, it's exactly like a coherent state of the, so it's the free part of the Hamiltonian, right? So if you think about the free Hamiltonian for a quantum field, that is identical to the free Hamiltonian for the harmonic oscillator. So you can just map that exact construction from one to the other. Okay? Anything else? Yeah.
So whenever you say coherent state and Fock state, in the back of my mind, I'm thinking like the Fock state is an eigenstate, so in the free space I have a single wavelength wave, and when you say coherent, I'm smearing it, like it's like a wave packet connecting
No, 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 no. So good. Yeah. So in the case of the harmonic oscillator, which is the particle harmonic oscillator, right? You are well, even there, right? Like if I think about the actual wave function, those states are still localized, right? But for the specific quantum field we're thinking about, right? It is in fact true that if I think about my, plane wave state, this AK dagger, the energy eigenstate, those are genuine plane waves. They're like all over the place, spread everywhere, right? A coherent state also does not have to be localized, right? It now depends upon exactly how you construct it. It can be localized, but that would again be the statement that I added a bunch of different Ks together, right? But so it's not the spatial behavior that's important as much as its temporal behavior, right? Because a coherent state is in fact a sum of a large number of these Ks together, okay? And that's kind of, so in some sense, your intuition is right, that a sum of a large number of Ks will have a more narrow, or no, at least a more interesting dependence on X, okay? So there is part of that intuition that's right, but essentially it's still the case that they don't have to be super localized. They can be like pretty spread out, okay? Anything else? No, good. All right. So let's think about how scattering works and why there's an important difference between these two cases. First of all, when I do scattering theory, okay, I'm always imposing energy momentum conservation, right? That's something that I do. Why do I do that? Other than the fact that someone told you should do it. What is the math that tells me that I should conserve energy momentum? So let's be a little practical, okay? Let's talk about an actual operator. So let's say in my Hamiltonian or my Lagrangian, I have the operator, say, phi of x, psi bar of x, psi of x, okay? That's some term in my Hamiltonian, okay? And, or the Lagrangian, the way you guys often think about it. So why do we get energy momentum conservation? So let's jump to that. I'll remind you of the story, right? Right, right, right. Very good, very good. So what the gentleman's pointing out is that the computation that you're actually doing is some perturbation theory calculation. Okay? So what you're actually doing is that you say I have some Hamiltonian H, which is equal to some H naught, which is some free Hamiltonian, okay? Plus some perturbation that is some lambda times, H interaction or something, okay? Look, I'm not going into detail about all this math because you can look it up, right? But I want to get the idea, much more important. So you have some lambda interaction, and what you're calculating is some transition. You're basically saying, I gave you an energy eigenstate, let's say K, to start with, and I want to go from K to something else, right? So you're always calculating the transition matrix element T, which is basically some K prime H interaction K, right? That's what you're actually calculating, right, in all of your computations. All right? And so if this transition matrix element is 0, nothing happens. If the transition matrix element is non-zero, something will happen. Okay, so that's all the math you need to do. So let's now think about how this operates for a coherent state versus a Fock state. Okay, so let's be a little bit explicit about it. Let me erase this stuff here. Okay, so what's going on there is that I've got my interaction, let's call it phi of x, psi bar of x, psi of x. This is my interacting Hamiltonian. And I'm going to write this in terms of my creation relation operators. So I'm going to write this as some integral d cubed k1, okay, d cubed k2, d cubed k3. This corresponds to the three momenta of the three fields that I have in there. So I can write this as a k1, okay, e to the I k1 dot x plus a dagger k1 e to the minus I k1 dot x, and then multiplied by, let's call it bk1, okay, e to the I k2 dot x plus b dagger k2 e to the minus I k2 dot x. And then another thing which is bk3 e to the I k3 dot x plus b dagger k3 e to the minus I k3 dot x. Okay, so the two b's, they correspond to the creation and annihilation operators for psi, and they correspond to the two different momenta k2 and k3 that are in the problem. And A corresponds to the creation and annihilation operators of phi. Okay, so what we do is that in reality this is the Hamiltonian density also. So the true Hamiltonian contains an integral over d3x, which I forgot to write. Okay, so this is what I actually am doing. So this is my full perturbation theory. Okay, so now you combine all the terms together and you end up getting an integral d cube x, d cube k1, d cube k2, d cube k3, and then you have got a bunch of products, like you got, for example, ak1, okay, bk2, bk3, okay, e to the I k1 plus k2 plus k3 dot x. Then you get a dagger k1, let's say, bk2, bk3, e to the minus I k1 dot x, okay, plus I k2 plus k3 dot x, so on and so forth. What do I want to do with all this algebra, right? This is a crucial part. If something non-trivial is supposed to happen, I have to use these operators to calculate this transition matrix element, and that's what will tell me what's actually going on. Okay? So now let's think about this, right? So what does this operator a dagger k, bk, bk3 mean? It will allow me, for example, to create a phi particle and destroy two b particles. Okay? So if I gave you this quantum state, let's write this here. If I gave you this quantum state that were basically two, so these are both psi particles, okay, let's call it psi, and I want to figure out if I can produce a phi particle, okay, let's call it k1 phi, and I use this interaction Hamiltonian hi here, this is the transition matrix element, and what you now see is exactly the thing, right? Because I've got bk2 and bk3, those guys can go and swallow up the two psi particles, and I can use this a dagger to create a phi particle, right? And in doing so, I have to perform this integral over all space, and the integral over all space gives me this factor over here, e to the negative I k, right? This is proportional to integral d cube x, e to the minus I k1 dot x times e to the I k3 dot x, e to the I k2 dot x, and that integral is the well-known delta function. So that ultimately tells me this entire thing is proportional to delta of k1 minus of k2 plus k3, right? And that's your energy momentum conservation. So if I am sticking with my Fock states, okay, the only way I can get something non-zero is if this energy momentum, if that transition matrix is non-zero, and that locks me into energy momentum conservation, okay, which is all the stuff you've already heard about. All right? Let's now ask exactly the same question with the coherent state. Okay? So suppose we have a coherent state. Oh, and by the way, a crucial thing I should have mentioned, right, is that precisely because of the fact that these guys are of the form A plus A dagger, right? If I have any Fock state, right, which is an energy, which is an eigenstate, for any Fock state, it is in fact true that if I do n A plus A dagger n or A minus A dagger n, all of these all the transition matrix elements are zero of this kind. Right, we already saw that in the case of the harmonic oscillator. So for a Fock state, the only way I can the only way I can get something non-zero is for me to change particle number. Right? If the particle number is locked between this side and this side to be the same, these products are zero. Right? Which again shouldn't surprise you because the Fock states are supposed to be energy eigenstates, so they cannot on their own change particle number. Something needs to actually happen. Right? But let's think about for a coherent state. So what I'm going to do now is for phi, because phi is my boson here. I'm going to give you a coherent state for phi. Okay? So suppose we have a coherent state for phi. Okay? What does that mean? It basically means that I've given you a state which, for let's say the momentum k1 is an eigenstate of ak1. Right? So I'm going to give you a state alpha, okay, which when ak1 acts on it gives me an eigenvalue lambda of alpha k, let's say, okay, let's call it alpha k, times the same state itself. Okay? So now let us do exactly the same calculation, but I'm going to now at this point not change the coherent state. I'm going to retain the coherent state as is. I want to know is it a transition or not a transition. So I'm going to now calculate, okay, what is this quantity, which is alpha k phi alpha k. Right? That is a transition matrix element I could calculate. And what do I find? Right? This is going to be equal to, at this point, alpha k, and this phi is some linear combination, let's call it ak plus or minus, whatever, ak dagger, right? Alpha k. And the crucial thing is that this is not 0 anymore. Right? Because when ak acts on alpha k, I get an eigenstate back again. And you can also convince yourself that an a dagger acts on this guy, you get its complex conjugate. So this quantity is non-zero. It is simply equal to lambda alpha plus lambda dagger alpha k. Okay? So if you perform exactly the calculations that you're doing for your usual scattering, right, by which I mean the true thing you're always doing is computing the transition matrix element, and now you find out that if you calculate the transition matrix element by simply changing what quantum state for phi lives in, you have found that you are no longer bound by energy momentum conservation, right, because that part of the integral no longer shows up. Okay? So that is a formal mathematics. But anytime you understand formal mathematics, you should also have a bullshit way of explaining it. Otherwise, you're not a real physicist. Right? So what is the bullshit way of understanding this? So anytime there is an opportunity for bullshit in quantum mechanics, what principle must you be thinking about? Uncertainty principle. Very good. Exactly. Okay. So let's think about the uncertainty principle and how it is tied to the uncertainty principle, right? So what is it about a Fock state or a that is very certain? Energy and therefore particle number, right? So when I think about a Fock state is a state with a well-defined energy because there's an energy eigenstate. That means you know exactly the number of particles there are. Okay? This coherent state is definitely not an energy eigenstate, right? Because that's the whole point, right? So therefore, you don't really have an exact number of particles associated with it, right? What's more is that the coherent state is a state with a well-defined phase. Now, I didn't prove that to you, but you can, when you go through algebra, you can learn that on your own, okay? What that means also, to the similar kind of bullshit stuff that we often use, there is another uncertainty principle that basically says the uncertainty in number times the uncertainty in phase is supposed to be order 1, right, greater than or equal to 1. And that means when you have a state which is maximally well-defined in phase, its number of density is maximally uncertain. Okay? So when you're trying to do energy momentum conservation, right, that statement is only meaningful if you actually have a well-defined momentum or well-defined energy for your incoming state. Otherwise, what are you even talking about? Right? So what you learn is that if you're doing exactly the same calculation with the coherent states, precisely because the coherent state has no well-defined number, right? It has no well-defined energy momentum. Therefore, you're allowed to, in some sense, violate energy momentum conservation maximally. Now, that's bullshit, right? But the correct mathematics is what I gave you, which is that, in fact, if you do the actual calculation, you see you're not doing anything different from what you're normally supposed to be doing, right? It's just that your quantum state is very different. Okay? And that is what allows you to play the games that we're going to play now. What is the game we're going to play? Right? So the game we're going to play is basically say that, look, when I'm thinking about my detection idea for ultralight dark matter, I don't want to do all this fancy schmancy quantum stuff, right? I just want to think about it classically. And how am I able to do that? Let's see the algebra for it, which is exactly going to be this stuff. So what I want to do is to basically say there is some phi field in my Hamiltonian, which is integral d cube x, phi of x, psi bar psi. Okay, so let's say phi is ultralight dark matter. Okay, and the psi is fermions like you and me. Okay, and what I want to know is how do these fermions respond to the ultralight dark matter? Okay, for a Fock state, you have to do scattering. And now let's see how I can easily get the answer for the coherent states without having to worry too much about the quantum mechanics. So I want to understand how these states evolve, right? So here is the main point. When the dark matter interacts with me, the dark matter is not changing, right? It's changing very little. So I want to say, okay, the quantum state of the universe is basically some kind of product state that we think it is. So there is some states for the fermion, okay? There is some quantum state for phi, for psi, okay? Let's call that S of psi, right? So this is some quantum state for the fermions, okay? This is some momentum or whatever it is, right? S psi is for the fermions. I don't know why I picked S, maybe for Surjeet, who knows, okay? And I'm going to now give some coherent state for the boson phi, okay? So this is some basically alpha k for phi, right? That is the quantum state of the universe. Let's call it sigma. And I want to time evolve I d sigma dt is equal to h sigma. This is the actual calculation I'm supposed to do, okay? Now what I know is that I know that this phi hasn't changed too much, okay? So I'm mostly just interested in what's going on for the psi field. And so what I'm allowed to do to understand what's going on is to take some inner product, right, just to get the answer that I want. So what I can now do is the following. I can now calculate, let me put that up there. I can now calculate okay, let me take alpha k, this inner product, right? There's a trick that we do all the time, which is now equal to, I want to figure out how this evolves. Yeah, let me just write it more properly. I've got I d sigma dt, h sigma, and let me take the inner product of this equation with my state alpha k. Right, that's a thing I can do, right? And what this allows me to do now is if I substitute for what's going on here, this will contain terms of the form integral d cube x, and I end up getting phi of x, psi bar of x, psi of x, and then I have my sigma. Sigma is now basically phi of x, sorry, the quantum state. This is, what did I call it? Yeah, S psi of k. This is my fermion, and then this alpha k of phi. And I've got my alpha k of phi sitting in here as well, right? And now you see the trick, which is that I can now move this alpha k inside. There's a phi of x acting on this guy. So this basically becomes integral d cube x for all practical purposes, alpha k of phi, phi of x, alpha k of phi, okay? Psi bar of x, psi of x, still acting on this fermion field. I'm now allowed to replace this expectation value by the classical field, which is this, the lambda that I put in there, lambda of phi plus lambda dagger of phi is a classical field, okay? Psi bar of x, psi of x, so on and so forth, right? So the key point I want you to take from this is that it is this algebra that allows me to replace the phi of x operator by its expectation value, which is this quantity, in whatever quantum state that I'm in, right? And it is that expectation value which is your classical field, which you write as phi of x cosine omega t, things of this kind. Does this make sense? Right? I realize I've jumped a little bit into, because I don't exactly know your true backgrounds, what people know, what people don't know. But I'm willing to bet that if you don't know something, there are other people also who don't know something. And in fact, a lot of what I've told you is something that is highly confused in the literature. Not everybody thinks it's true. So if you have any questions about any of this, right, there's no shame in asking. You want me to go over something again? I can. Right? I'm here for your sake. It's not for me. Yeah. Okay. No, that's fine. That's fine. No problem. Yeah. That's right. Oh, that's probably just because my bad notation. Sorry. Yeah. I just screwed up a notation. Sorry. Yeah. So that's right. That's screwed up. Yeah. So these are just two different things. So let's even call it. So I'm just saying that I have a specific quantum K, okay, and it is just like some other state of the fermion. So this is the state of the fermion, and this is the state of the phi. So the Ks are not the same. Okay. So the last bit we're talking about is basically saying, right, that maybe I'll step through this a little bit more slowly, right? What I'm trying to say here is the following: that I want to simply evolve this state sigma. Okay, so I do I d sigma dt is h sigma, and I want to evolve the state by under the condition that my phi field is not changing too much. So I'm going to say that the phi field is alpha k, right? And I'm simply trying to understand how does my quantum state for psi behave in the presence of phi. Okay, and so that allows me to do the inner product, which then means I can convert this operator that sits in there and replace it by its expectation value, which is what I actually have in this case. And that expectation value is precisely the classical field. Okay. Now let me connect this to be more familiar with what you kind of may have seen in your previous treatments about quantum mechanics, which is the following thing. That how many of you have seen the treatment of the two-level atom in the presence of an electromagnetic field? It's called the Rabi oscillation, things of this kind, right? So let me remind you of something that you've probably seen before, because I want to connect it all, right? If you have a two-level atom, okay, or just in general, actually, let's even forget about something as complicated as that. Let's just talk about something called the Stark shift, right? The Stark shift is a statement that if you have an atom and you apply an electric field, the atom will respond to the electric field, right? That we all know, it stretches, right? How did you calculate this? What you would write down is a Hamiltonian for the electron. So you would say this Hamiltonian is something like negative p squared over 2m for the electron, plus some potential, right, for the electron from the nucleus. And then you say there is an electric field component, right? You would basically say this is some epsilon, okay, times the electric field dotted into the r coordinate or whatever, right? That's how you calculate this guy. When you are doing this calculation, you use the word semi-classical, I'm sure, right? And usually when people write, they don't define what that means, okay? But what does it actually mean? What it actually means is that you are thinking about the electron quantum mechanically because you're trying to find the electromagnetic, the energy eigenstates of the electron under the presence of this. But you, of course, were not thinking about the electromagnetic field in a quantum way, right? You simply replace that electromagnetic field by the electric field, right? It could be, if it's oscillating, you'll be thinking about a Rabi oscillation. If it is a static electric field, you just put the electric field that someone gave you, right? What gave you the right to do that, right, is precisely this mathematics. Because what you did was, in reality, the electromagnetic field, whether it's coming from an oscillating laser or it's coming from some dude creating an electric field, is a quantum state of electromagnetism. It is, in fact, a coherent state of electromagnetism. Okay? So what you were actually doing in doing this calculation is that you were supposed to have done this. The electromagnetic field and the electron are both quantum systems. So you, in fact, were supposed to do I d sigma dt is h sigma. You're supposed to do all this algebra, and then you learned that in reality the electric field was a classical object, that is, it is a coherent state, and that meant you could take this inner product And by taking that inner product, it meant that the electric field that lives in here was really the electric field operator, which then acted on the electric field state of photons, whatever it is, which is I called it as, let's call it alpha of the electric field. And it is this magic algebra where you computed the expectation value on this coherent state, which allowed you to convert this operator into a classical field. Okay? And so you put a classical field and you forget about all of quantum mechanics and you just simply say, look, in the presence of this classical field, let me now try to understand how my electron behaves. Yeah. Well, if alpha was now you have to tell me what kind of state it is, right? So if it is a Fock state, which is a state of definite photon number, that is 0. Yeah, if you do a conventional Fock state, this, this thing is just 0. A linear combination will not, right? So the point is, it's about what limit you're interested in. So the point is that if you're giving me a pure Fock state, I always have to get excitation. Whereas if I give a linear combination, of course, that, so the moment you get a linear combination, your particle number is not exact anymore. And the moment your particle number is not exact, you can replace it by, well, it won't be the true expectation value. It's a question of how good the limit is. But you can then deviate away from things like the scattering limit. It need not be a coherent state. No, if you do it, so this is the thing, right? It's a question of when is the limit truly accurate, right? So it's only, so this entire calculation, you can always do that, but it's now a question of like, at what point is my limit actually accurate? And that's where the coherent state becomes important. Good. Yeah.
We started by evaluating the Schrödinger equation for the evolution of this cat state of the universe.
Yeah.
We multiply it by a graph.
Yeah.
And then at some point, part of the graph and part of the cat,
they marry together. Yes.
But then I end up with just a cat state.
Yeah. So in reality, right, what I should have truly done is I should have also, what I've not done here is I have not told you what's going on with the psi fields. Right? So I'm using this to understand how psi reacts. Okay? So what I really did was, truthfully speaking, I didn't tell you what the psi operators were. Right? So now you can basically give various psi fields here, psi states, and that's the true calculation, right? You'll be like, oh, how does my psi actually evolve? And so the whole point here is the fact that when I've replaced this by this expectation value, the psi operators are still as operators, so I can now tell you how psi is going to evolve. Right? It is exactly like this story here, where I've been able to replace the electromagnetic field operator by its expectation value, but I did nothing at all for the electron. So if I want to understand how does the electron respond in the presence of a classical electric field, by which we mean the state, I treat the electromagnetic field as a classical quantity, and the electron states are still electron states. Right? Because what I did here was a partial trace, if you will. I kind of just did part of the system. Okay? So good. So yeah.
So to summarize, we're making the case that semi-classical treatments of electromagnetism are only valid because of the existence of coherent states.
Absolutely. Exactly. Okay? Yeah.
This special with the property of A applied to alpha equals to their value.
Yeah, very good. Yeah, I didn't labor through this too much, but that is kind of tied to what Marco's question really is. Okay, good. So let's be a little bit more slow about it. So the whole point always comes down to when are these overlaps 0? When are they not 0? How big are they? Right? If it's very small, we don't care. Okay? The crucial point is that if I gave you a state which is an eigenstate of this guy, then A plus A dagger acting on alpha is simply this lambda alpha plus lambda alpha dagger. Right? That is, when I took this state and I removed a particle from it, let's think about it very physically. Right? What does this statement mean? It means that when I have my quantum state alpha and I have the annihilation operator act on it, I ate a particle, right? Yet the state did not change. That's why it's an eigenstate. Okay? So this means, right? And again, this math is still correct, that this is true, right? So I want to distinguish that from just say a typical linear combination. Let's just do it practically, right? So that's true. So let me give you another state, which is basically a state of this kind, a state psi. My notations are terrible, so let's call it sigma instead. So that's another style you may confuse it by. Let's call it C1 of K1, okay, plus C2 K2, right? This is some superposition of K1 and K2, okay? I want to understand how is this state different from the evolution of these annihilation operator states, okay? Now, you're absolutely correct that if I look at this state and I calculate, you know, some whatever operator phi on sigma, right? This combination will in general have a non-zero eigenvalue. Sorry, a non-zero transition matrix element, right? Because this will now be something of the form, you know, K1, whatever this is, C1 plus C2 K2, okay, phi C1 K1 plus C2 K2. Now, one thing to note, of course, right, is that when I give you a simple superposition of this kind, right, unless K1 and K2 are right next to each other, this is still 0, right? So that is another way in which the coordinate states are different, okay? But more than something trivial like that, because now you might say, give me more and more complicated superpositions, ultimately you will get to a coordinate state doing that way. What I want to emphasize, which I didn't discuss before, is a slightly different statement, which is coming down to the understanding of how time evolution itself treats coordinate states differently from Fock states. Like, what is the fundamental difference between the two? And let's talk about that for a second. Okay. So, in the case of the simple harmonic oscillator, right, when we learned A alpha goes to lambda alpha, something of this kind, you were probably taught something like, you know, that this is a minimum uncertainty state, stuff like that, right? That is typically how it's taught, right? But there's something more important about these states, which is the following, right? Let's actually use this to understand our world itself, right? Typically, when you have a quantum state, right, this is a big challenge for quantum computing, for example. When that state interacts with the environment, it gets messed up, right? You'd say entanglement, this, that, whatever. What kind of quantum states of photons do we normally see around us? So I see photons, right? Huh? Not zero energy. So like when I look at photons in my world, right? So what quantum states are they typically in? So we've talked about two states, actually. So you should know the answer, right? We have seen Fock states of photons, which because I see light from this tube light or whatever, or light from the sun, light from an incandescent bulb. Those are all Fock states, as we argued. And you should not, of course, be confused that you're seeing a Fock state, because a Fock state is an eigenstate of the free Hamiltonian, right? So if I give you the photon particle, that photon particle will freely propagate in space because it is an eigenstate of the free Hamiltonian. So you're not surprised by that, okay? The other kind of state that we see in our world is the coherent state, right? Because clearly lasers exist, right? Clearly radio waves from coherent states exist. Now, that should actually make you think a little bit more, because these are not energy eigenstates, right? And yet, if the world had, of course, no interactions, there's nothing interesting about it. It's like, whatever, you gave me a weird quantum state. But the fact of the matter is, even in the presence of all the interactions that we see around us in the world, these states still make sense, right? As in, like, when a radio guy, so think about it, right? So usually if I'm trying to give you some very complicated superposition of quantum states, right, you have to work super duper hard to protect that state from the environment, okay? But clearly when my radio station is sending me radio waves, they're not doing anything, right? They're just like doing that. Okay? So why is it that a coherent state of this kind is able to survive the environment? What about it is so good, so protective?
Isn't it that by the certain decrease, where you have maximum uncertainty in the energy, so you have maximum localization time?
Well, that is a bullshit argument, yeah. But I want the mathematical argument. Yes, I will come back and say exactly what you said, but I want you to tell me in like because the problem with the bullshit argument is that you could use Marco's question. You could be like, look, I gave you some other superposition, right? So
Can I just ask a question?
yeah,
No, because you said that this whole business works just because of coherent states. But I would have said that coherent states are the states that make this business as credible as possible.
right. So I want to know the yeah, like the defining feature of it. Yes.
Is it essentially that the environment is like mapping a bunch of creation and annihilation operators onto your system, but obviously it's the state that's the eigenstate of the creation?
That's right. That's the right way of saying it, right? Which is the fact that the defining characteristic of a coherent state is the fact that when I'm trying to do something to it, like eliminate a particle, it doesn't change, right? So what we are asking for is basically saying that yes, when I have a free system, no interactions, the Fock states are fine, right? But what we're actually asking now is saying, look, I have my world with maximal all kinds of interactions turned on. What other state, okay, is automatically preserved under time evolution? It has got to be a state where even though the interactions are constantly happening, the state never changes. Okay? And what is the state that never changes no matter how the interactions happen? I have to go and look at, well, how did I actually go and construct my interactions? My interactions are all constructed still from this free basis that we're talking about, but that specifically tells me that the states of interest are states that do not change in the presence of an interaction, and that is precisely states which are the eigenstates of the annihilation operator. Okay? So it is only those states that will remain that way. So I should wrap up with this, I guess, even though I didn't get to what I wanted to say, but I think this is important to set the story, which is the following question, right? Like, so what we are asking is that, let me go to the early universe, okay? Let me go and produce whatever quantum states I can produce. And let me ask, what are the quantum states that will evolve in a simple way, okay, where interactions don't mess it up? So clearly, if I produce particles in definite quantum numbers, I know those will evolve that way. Let me now produce a superposition, okay, and see what happens to them. What happens to them is the following, right? If I gave you this quantum state sigma, which is a superposition C1 K1 plus C2 K2, so I worked very, very hard to create, so much of K1 and so much of K2, okay? That particle is not by itself. It's going to go and scatter with a bunch of shit, okay? So this guy, let's call it, it's a state of the phi particle, right? This is a phi particle, so let's call it phi. And this phi particle is going to go around and it's going to scatter with a bunch of psi's that are around. It'll do whatever, right? What's going to now happen is that if these are these kinds of Fock states we're talking about, right? These are like specific scattering events. So what will happen is that the quantum state of the universe will now become basically the C1, okay, let's call it K1 star phi and P1 star psi plus C2 K2 star phi and P2 star psi. What do I mean by that? Okay, so this guy, this K1, comes and scatters with psi and goes outward with a momentum that I called K1 star. So this is K1 coming in, scatters, and this guy goes outward as P1 star. Let's say the incoming was P1. Okay, and similarly, the K2 guy will come and scatter and go as K2 star, and this will become P2 star and P2. Right? So what will happen is that your quantum state basically becomes a complicated thing where your initial superposition, K1 plus K2, will scatter off, Some of the wave will go as K1 star, P1 will be entangled with it, the other guy will be P2 and entangled with it, so on and so forth. Okay? So that is a natural evolution that will happen. And this will keep happening unless it is the case that the initial state was a coherent state of phi. Because if the coherent state of phi, precisely because this interaction preserves it, it's possible for you to end up with a state where phi never changed and psi just moved in some other way. Right? So that is exactly the way in which we realize that, look, the two quantum states I see in my world are typically either Fock states, because for the Fock states, this is what will always happen. Right? Whereas for the coherent states, this other thing happens. Okay, so let me put it all together back to you, right? Which is like we talked about, how is the CMB different from the radio station? And the CMB, what is actually going on is that in the early universe, I'm not producing a coherent state, or some thermal state. I'm basically having a whole bunch of scatterings occurring all the time. And so what that literally means is that when these things scatter all the time, right, my CMB photon that is coming in with some momentum K1, which I observe in my CMB detector, is in reality entangled with some electron it scattered 13 billion years ago. Right? So the true quantum state is going to be the fact that this CMB state of momentum K1 is tied to some electron of momentum P1 that it scattered with 13 billion years ago. Right? Plus there is a CMB quantum state of K2, which is entangled with a different electron that is scattered with it at P2, I guess, a long time ago, so on and so forth. So the CMB is a superposition of these entangled states, and we are entangled with one of them, and that's why I always just see specific particles in the CMB, right? Whereas a radio station is a coherent state. Okay, so before I finish, I just want to mention for ultralight dark matter, right? For all of the experiments that we're going to talk about, okay, from tomorrow or whatever, all of these experiments are based on the assumption that I can replace the dark matter field operator by the classical field value, which means all of those dark matter stories only make sense if the ultralight dark matter is in fact in some coherent state. Because if it is not in a coherent state, I cannot do this trick. I have to do scattering. Okay? If I have to do scattering, yeah.
But if you are worried that if it's a coherent, if you put the photons, let's say, to change the state, because scattering we read that happens too often, no?
Sorry, say that again?
The scattering we read that happens too often with,
Yeah, it'll be very rare, exactly, yeah. Not only will it take a long time, it is also the case that the energy momentum conservation will come and bite you. Right? So the crucial point I wanted to get to, right, which I said earlier, is that if I do a scattering process with a nucleus, like you do in a WIMP detector, right, you realize that the energy in the nucleus, which is what you're actually observing, is actually momentum squared over the nuclear mass. And as the momentum gets very small, which it does get for ultralight dark matter, right, it's impossible to do anything. Okay? So all of this has been about dark matter, but I also want to again, talk about physics that matters, like physics to a standard model, right? So there are two kinds of great challenges in our world. One, let us say, is the experimental discovery of gravitational waves, right? The other, that's a solved problem, as you all know. The other is the detection of the cosmic neutrino background, right? Which is an unsolved problem, as you all know. Now, it should make you think, right? The cosmic neutrino background, the neutrinos are interacting with us through the weak interaction. Gravitational waves interact with us through gravity. Isn't it fucking crazy that we've been able to detect something that interacts with us through gravity, but not through the weak interaction? Okay? And let's even look at how absurd it is, right? A gravitational wave that the guys at LIGO are seeing, they are seeing particles with a frequency of around like 10 hertz. Okay? That's what they're seeing. So what is the energy of 10 hertz, or momentum of 10 hertz? The momentum of the gravitational wave is 10 hertz. A hertz is about 10 to the negative 15 eV. So this is about 10 to the minus 14 electron volts. The neutrino background, okay, is something like, let's call it milli eV. So if you did not know about quantum mechanics, okay, and you just said, okay, look, I'm just an energy guy, I do order of magnitude physics, which is a great thing to do. You would say, look, this dude is milli eV in energy, is interacting with us through G Fermi, which is basically 10 to the minus 5 GeV squared. That dude is interacting with, as momentum 10 to the minus 14 eV per graviton. And its cross section, my God, is 1 over m Planck squared. Right? Yet, factually, it is true that we have detected gravitational waves, and nobody has any idea how to do cosmic neutrino background. The key difference is the quantum state, right? If the gravitational waves from LIGO were thermal gravitons, right? You could have imagined that there is some star out there shooting thermal gravitons at us. For all those thermal gravitons, if you go and calculate the expectation value of the metric, right, the graviton state h mu nu, okay, thermal, let's call it T, that will be 0. Okay, LIGO would have to do scattering of individual gravitons. It's not going to work. But fortunately, the gravitational waves that are produced are actually coherent sources because there's big stars going on each other. They produce coherent gravitational waves. And so what LIGO does is that they are going to actually replace this guy by the classical gravitational field, H classical, which is some cosine omega t minus omega x and blah, blah, blah. And that is what they're literally seeing when the mirrors move back and forth. Whereas, unfortunately, for the cosmic neutrino background, because the damn thing is a fermion, right, you don't have same kind of coherent states. You've got actually, you produce them thermally in the early universe. They're like the CMB, the C nu B, right? So those guys, because they are these Fock states, you are tied to detecting energy momentum conservation. And that is one of the big challenges in what you can do, right? So the key takeaway from this discussion is the fact that there is an enormous difference between coherent states and Fock states, exemplified by the numerous examples that I gave you. And when you are in a coherent state, okay, your detection possibilities are dramatically different because you can just replace it by the classical field, which is what I'll talk about in the next set of lectures. And the reason why you can do this is precisely because there are production mechanisms for ultralight dark matter that produce coherent states. That's kind of what Marco was alluding to, the so-called sort of misalignment production and this and that. Okay, but that's a central part of understanding why this is possible. So we'll continue about this from the next lecture. Yeah. It's in fact the classical field. So that when you say A naught cosine omega t, right? So in field theory, it becomes the classical field value that you write down. Yeah, yeah, that's right. So what you end up getting is basically, right, like, so the eigenvalues themselves are complex because A is not Hermitian. So what you see is, but what you always get is a combination of lambda plus lambda dagger, things of this kind. So the imaginary part dies off, and what you end up getting is the, what you would call the classical position or classical momentum of the object. In particle mechanics and quantum field theory, it is the corresponding classical values of the fields that it corresponds to.
So you ask if it's an eigenmode also of A dagger?
No, it's the conjugate of it is. So you've got, like, if A alpha is thing, alpha A dagger will be the eigenvalue. So it's whether on the left or the right. Yeah.
Is that when you do the trick at the end, you do the stick and you go in a state, there is like a correction that you can write
Yeah.
state as green state plus correction.
Yeah. So the corrections are very small. So this is where the large occupation number comes in. So you can show that when you're actually doing those calculations, right, the corrections would go as like 1 over n, but n is the number of particles that you have. Okay, so a formal question would have been, look, everything I say is also true for the vacuum, right? Because vacuum is also an eigenstate of A. Okay, so why does this not work for the vacuum? And that's precisely because of the vacuum, the occupation number is small. So the quantum corrections or large. Whereas when you have a classical state or a coherent state with a large occupation number, large intensity, those numbers will die off. Yeah.
How would you think about gravity waves from inflation? Would you
Ah.
say that the
Ah.
computational valuation
Yeah.
for gravity waves, ultimately, are looking always at quadratic quantities. So this discussion
No. See, for gravity, see, this is a very important question, okay, which again gets to the production mechanism, right? So what's happening for gravitational waves from inflation is the fact that when you produce it, you're actually in a Fock state. You're in a vacuum. What happens is that during inflation, that mode goes outside the horizon, right? So that's a way in which you're actually going from the adiabatic limit, which is when you produce it, it's like a small thing, and then you go to the sudden limit. At that point, what's happening is that there's a sudden approximation change that actually happens, which results in the following thing. You basically reduce the uncertainty in the phase because the velocity of the mode goes to 0, which actually maximally amplifies the uncertainty in its number in its like classical number density. So you basically classicalize.
but still you will have that expectation value that you're running there will be zero.
Will be non-zero. No. Yeah. So it is, well, it is 0 for a somewhat different reason, okay, which is kind of the stochastic limit.
Classical light equation number, okay.
Yes.
So, but on the other hand, it's still fully quantum.
No. So once it is classicalized, that expectation value is non-zero, right? So there is a different way in which it's 0, which is a statement that basically if I average over the full ensemble, then it is 0 due to the fact it's a stochastic gravitational wave. It's coming from many different directions. Okay? Yeah, but and it's also the truth that when you're actually entangled yourself to a specific value, right? So yeah, you've got to be a little careful about what is being meant here, right? So in inflation, what's true is the fact that yes, I start with something with expectation value of 0, and when I time evolve, if I compute the full expectation value, it will still remain 0. That's what you're saying. But what that really means is the fact that there are different observers. One observer gets entangled to one value, different observer gets attached to a different value. Okay, and if you do an ensemble average over all the observers, it's 0. But for any specific observer, it is not.
But when is it becoming non-zero? Because when I do the computation of inflation, it's still zero.
No, but see, that's because you're computing the full expectation value, but not for a specific measurement or a specific direction.
But I'm not measuring anything. Just one mode.
No. So there's the thing, right? When the mode goes outside the horizon, right? What ends up happening is that you end up getting a world which is like this complicated superposition, where you would basically say that say this is a mode and the mode exited the horizon, okay, and you end up getting a superposition which is basically one wave went in that way and got amplified. Okay, so let's call it again, bad notation, I guess. So let's call it K1, okay? So you want K1 became classical, okay? And that gets sort of entangled with some other state that eventually becomes U, right? So this is U will think this is K1. Then this mode went on this side, the same guy, but it went on that direction and got amplified. So that'll become this, K2 classical that way, and you get entangled this way. Right? So if you compute the expectation value in the full state, it will still be 0. But you would say, look, I am this observer. So when I go and calculate this guy, this will be non-zero. Yeah. So it's like basically, right, like we have the...
Is it really kosher, when I consider, for example, the fact of gravity waves in the CFT, to use the classical?
It is, because the fact is, these worlds don't talk to each other, right? They're just sort of orthogonal to each other. And so it is simply the statement that you realized this specific fluctuation in your world, which was your CMB. And so the gravitational wave... Yeah, sure. Yeah, but it's a delicate question, though. Yeah.
Because these two states, I'm measuring both of them.
Yes, you are in both of them.
Yeah, and then they came back.
They don't, so they come back in, but you can't see.
Interact with me.
No. So see.
Maybe this conversation can be answered.
Yeah. There's a lot to talk about. Yeah.
Are there any additional questions? If not, I think we can continue.
Let's remain coherent. Yeah.